In our next topic, we are going to introduce wireless frames. This will start with a discussion about the flow of packets in the connection setup process of wireless networks. This will be followed by a discussion about the components, structure and lastly the different types of wireless frames. Now coming to our first item for this topic, we are going to briefly discuss about the flow of packets required to connect and start data transmission on a wireless network. At a high level, this is a 6-step process. As illustrated by the diagram shown on the screen, the first step deals with the transmission of a probe request packet from the wireless client. This can be possible in two different ways. Either the wireless client station can broadcast probe requests out all channels, trying to find a suitable access point it can connect to. Alternatively, if the client already knows about a specific network from its cache, which is a list of previously connected networks, it can send a directed probe request for that specific SSID. Access points advertise their availability to wireless clients by broadcasting beacon packets, as we will see later. In response to probe request from the client, the access point within the specific RF range answers back with a probe request packet. This packet contains additional information like the security authentication method expected by the AP. In the third step, the client station authenticates to the AP having the best wireless signal strength. The number of packets in this step varies based on the type of authentication being used. The authentication type can be either open or shared. We will talk about these later. The end result is that the access point will either send a pass or fail authentication response to the client. If the authentication is successful, we can move to the next step, the association phase. At the beginning of the association phase, the client station sends an association request to the access point. It also mentions the capabilities supported by it, like acceptable data rates, etc. Finally, in response to the association request, the access point sends an association response message to the client, if it can fulfill the requested capabilities. If all these three stages are successfully completed, the client can exchange data on the wireless network. Please note that this is an extremely simplified version of the wireless connectivity process. There might be other steps involved like challenge handshakes, key exchanges, etc. based on the different wireless configuration settings. In reality, all of this is implemented in the wireless connectivity state machine, where there is a defined transition from various states. For example, if a particular client is in the associated phase, which is state number 2, an access point, or even an attacker, can send a DAuth packet. This will take the client directly from state 2 to the unconnected state, which is state number 0, effectively bypassing state 1, which is the authenticated state. This ends our discussion on the wireless connectivity stages. Next, we are going to talk about the components of wireless frames. Now we are going to look into the basic structure of wireless frames and the notable fields and options present within those frames. Similar to Layer 2 protocol of their wired counterpart, that is Ethernet, wireless networks also refer to their Layer 2 or data link envelope as a frame. Wireless frames have the following basic components. The first component is the header, which contains various fields which are going to be described shortly. Next is the data or frame body section, which contains the actual data sent over the network, for example HTTP, ARP, DHCP packets, etc. The data portion varies in length based on the security protocol used, where 2324 bytes being the maximum length. Finally, the 4-byte FCS or frame check sequence is the CRC value of the frame, which is used for error detection similar to Ethernet. Wireless frames are based on the header structure shown on the screen. The presence of each of these fields in the header depends on the type of frame. Not all frames contain each of these fields. We will see the differences in fields utilized by various packets later. The first 2 bytes of the header comprises of a field known as the frame control field. This field consists of various subfields, which are depicted in the image shown here. Now we are going to present a brief description of some of the notable items within the frame control field. Protocol specifies the version of the 802.11 protocol being used, currently always set to 0. Type and subtype. These 2 fields define the type of the frame. There are 3 different frame type fields: control, value, 1, data, value, 2. and management, value 0. Within each type there are multiple subtype values denoting the specific function of the frame, which will be discussed later. 2 DS and from DS indicate the direction of the frame, meaning is it exiting or entering into the distribution system. More fragments is used to indicate whether more fragments of this frame are to follow or not. Retry indicates whether the frame is being retransmitted or not. Power management indicates whether the client station is currently in active mode, value 0, or in power save mode, value 1. Efficient power management is particularly important in low power devices fairly common today like cell phones. More data. APs use this bit to signal clients in power save mode that they have some packets waiting in their buffers for them. This prevents the clients from going to power save mode. Additionally, it may indicate that APs are going to send broadcast or multicast frames in the following packets. WEP or protected frame indicates whether or not encryption and authentication are being used in the frame. Last is the order field. It might be required for special traffic classes like voice and video that are conscious about the way packets are received at the other end. Now that we have looked at the various options within the frame control bytes, we are going to explore the remaining fields within the 802.11 WLAN header. First is the duration or ID field. This 2-byte field has different purposes depending on the frame type. In power save poll messages, they are used to specify the association identity or AID of the client station transmitting the frame. In all other control frames, the duration value is used for the network allocation vector, or NAV calculation. The NAV calculation is part of the collision avoidance technique employed by the 802.11 standard. More details can be found at the Wikipedia pages for the topics, network allocation vector, and carrier sense multiple access with collision avoidance. Next are the address fields. Unlike Ethernet frames which contain only 2 layer 2 addresses, wireless frames contain up to 4 layer 2 addresses. These additional addresses are used to specify the BSS ID, and to cater for the possibility of the frame being transmitted to, or being received from a distribution system. Control and management frames utilize only 3 addresses because they can never be routed both to, and from the DS. Depending upon the frame type, the 4 address fields will contain a combination of the following address types: BSS identifier, or BSS ID. As discussed previously, the BSS ID uniquely identifies each BSS. Destination address, or DA, indicates the MAC address of the final receiver of the frame. Source address, or SA, indicates the MAC address of the original sender that created the frame. Receiver address, or RA, indicates the MAC address of the next immediate station on the wireless medium to receive the frame. Transmitter address, or TA, indicates the MAC address of the station that transmitted the frame onto the wireless medium. This address is used when 2 APs communicate to each other, for example when using WDS. Next is the sequence control field, which consists of 2 subfields, used to manage duplicate frames and fragmentation. Sequence number, 12-bit, indicates the sequence number of each frame. The sequence number remains same for each frame sent. For a frame that requires fragmentation, fragment number, 4-bit, indicates the number of each fragment of a sent frame. As discussed previously, the type field defines the type of the WLAN frame, which are of 3 types: management, value 0, control, value 1, and data, value 2. Within each frame type there are multiple subtypes, which determine the specific function for that particular frame. Let's discuss each of these 3 types. Management frames are responsible for maintaining communication between the access points and wireless clients. They have the following subtypes. As we saw earlier, the probe, authentication and association requests and responses form the basis of the wireless connectivity state machine. These are subtypes 0, 1, 4, 5, and 11 respectively. Next are beacon frames that are broadcast by the AP to keep the network synchronized. They are usually sent at about 10 packets per second. They announce information like the SSID of the network, the supported rates and the other capabilities supported by the AP. Similarly, there are various other management frames like Measured Pilot, ATIM, Action, etc. Please refer to the companion guide for more details. Next are control frames. Control frames facilitate the proper exchange of data between wireless access points and clients. The following are some of their subtypes. Our first type of control frame is called Power Save Polling or PS Poll, which is subtype 10. Stations in Power Save mode awaken periodically to listen for traffic meant for them. If they discover that data is currently buffered for them at the AP, they will come into active mode and send a PS Poll packet to the AP requesting the transmission of this data. Consequently, the duration ID field in the wireless header contains the association ID, or AID, for the station sending the packet. Next are the Request to Send, RTS, or Clear to Send, CTS, frames, which are used to reduce collisions in the wireless air medium. Finally, an ACK frame is used by the receiver to acknowledge the sender that it has received the packet correctly. Next are data frames. Data frames carry the actual data set over the wireless network. The following are some of their subtypes. The first subtype is data only, subtype 0, which contains the regular data packets. Then we have the null data, or no data, which is subtype 4. Null packets are frequently used in power save mode. These three types of wireless frames also have some other subtypes which have not been discussed here for sake of brevity. Please refer to the IEEE 802.11 standard located on the IEEE website or the links mentioned earlier to know for more details about them. Please note that most of these frames have their own security weaknesses, which will be discussed later.